Hey everyone. Yeah, so my name is Joan. I'm a Netflix data engineer. And yeah, we'll present you how we designed a library that is currently powering all our quality of experience dashboards and more at Netflix. And so we used some unique Scala-free features that I think it's worth looking into. But before we start, why are we doing this? So this is the holy grail of video streaming. You want everything. You want the video to start fast. You want high quality, and you want no rebuffer. But kind of the cap theorem for database, you cannot have there's a laws of physics, I guess, that prevents you to have everything. So basically, if you want to start fast, you will have to probably give up some quality, or have rebuffers throughout the session. If you want no rebuffer throughout the session, maybe you'll have to build up an initial buffer, which will prevent you from starting fast, or maybe give up some quality, and vice versa. So if you want high quality, then maybe you need to build up an initial buffer, or you will have to rebuffer throughout the session. And so the strategy is going to be different depending on what video streaming service you are. For example, I guess YouTube, you kind of it's short videos. You want the video to start fast, otherwise you're going to switch to another video. It's maybe more acceptable to have rebuffers, because you might not even go through the whole video because maybe you're trying to solve some plumbing under your sink, and you just look at a video of someone who did that before, and you don't even know if that sink is that video is even talking about your sink or something. So for us, for Netflix, it's maybe more acceptable to take some time to start fast, but it's really unacceptable to have rebuffers throughout the session. And also, we want high quality. But yeah, we believe that we can push on all three of them. So how do we do this? So we're a data-driven company, like many, I guess. And what that means is that we're doing a lot of A/B testing. So we A/B test everything, from UI changes, recommendation algorithm, thumbnails, algorithm that selects the quality of your video, etc., etc. And to do so, we need to collect data. So I put together a super high-level and probably not even accurate kind of schema of how we collect data. So on the upper left, you would have devices. So here, TV, laptop, and phones, for example. Those devices, they stream video, and they also report logs about what happened over there. We also have our CDN, the Open Connect. We call it Open Connect, but it's our content delivery network that also sends logs to us to know what happened, if there was crashes and stuff like that. All of that ends up in databases. I just put 3 of them here. Playback logs, UI logs, and CDN logs, for example. And then we have a bunch of applications that are using this data for calculating QoE metrics, or measures, I should say. We have, for stream processing, we mostly use Apache Flink, and for batch processing, a lot of Spark. So if I talk about the first one, so streaming QoE, that's focused on the video part, like streaming the video. So things that we calculate are, for example, the play delay. Play delay is the delay between the time you ask for a movie to start and it actually played. We also calculate things like time to quality, the time it took to reach the highest quality, number of rebuffers, the throughput, etc., etc. App QoE, which is more about the catalog, the UI, it's going to be time to render, the time to render a page, the browsing duration, etc. We are also now a gaming company, so there's also other measures there. And we have more than 750 measures there. And I put the AAC simulator, which is an interesting case. AAC stands for Adaptive Streaming Engine. So this is not so little, but algorithm that you have embedded in your player. And this algorithm will choose, for example, when to start the video on your device, which quality to choose to download from the CDN, which server to connect to. So it does a lot of decisions. And it does some optimization, some interesting optimization. For example, let's say you have a scene where it's dark and you just see like kind of the shade like this. If you have a low quality here, you won't really notice the difference between like 4K or lower quality. And so let's say your internet connection cannot really sustain a video of 4K. What the adaptive streaming engine will do is it will purposefully downshift the quality to download this fast, and then it will go into the next scene, for example. And let's say the next scene is like fireworks, and it's like you need crisp quality because you will notice the downshift in quality. So now it has much more time to download that scene into 4K, for example. So it's like some tricks like that. And I can see the quality is not that good here, and this is because this is powered by YouTube, not by Netflix. Just presenting. All right, so back to this the schema. So we have a Spark job, which is this box here, which is the AC simulator. And what it's able to do is take data, actual data from viewing session, sorry, and also data from the CDN, and replay those with a different code of the engine, of the adaptive streaming engine. So the adaptive streaming engine is JavaScript code or TypeScript, and we embed that into the Spark job, and we're able to replay, for example, 1 million sessions in like half an hour or an hour. And we can tell, so the output is going to be the same as the streaming QoE app. So it's going to have play delay, the rebuffers, and so on. And we can compare that to see like what would have happened if we had this deployed into production without disturbing any of our customers. And we can assess if, yeah, it's doing better or not, all of that offline. All right, so what are the challenges with that? One challenge is discoverability of how things work. We have a lot of conversation internally on our Slack where someone would come and say, "Oh, how is the rebuffer calculated? How is this that? And how is the time to render, for example, calculated, and so on?" And people don't really know where it is on our GitHub because it's split by all those apps, you know. And so it would be nice if people could just like, you know, read the code. They know where it is. It's standard and it's easy to read. Yeah, so this is one challenge that we have. And once you have discovered the code, you might read it and you might find a bug in there that you might want to fix. So you might want to actually contribute it instead of like pulling into the owner of the code and you know, it's a long thing. Maybe he's busy and so on. You might want to actually add a new measure in there. And all of that, you know, it's not necessarily easy because you have to know where you have to add it, in which app. And yeah, that's another challenge. And also in terms of contributions, we have a wide variety of developers. We have data engineers, we have data scientists that contribute to that. We also have client engineers, which are more like front end. So all of that population is like used to different languages. And so you kind of have to like federate all of them. So for example, a mobile engineer might want to write a measure for how much battery did it use on the mobile during the viewing session. And so maybe he's working on optimizing the consumption of battery. And so they want to know if they're doing better or not. And the last challenge is reusability. So in the example where we have the AC simulator here, which outputs the same measures as the streaming QoE, it would be nice to share that code so that you get new measures, you get fixes all together. So it would be nice if there was a common library. So this is what we did, and we called it measures library. Why measure and not metrics? You might have noticed I'm mentioning measures since the beginning. A measure is, you measure, for example, the play delay in seconds. A metric is going to be an aggregation. So what is the average measure of, average play delay, or the median play delay, or the max play delay? Those are going to be all different metrics built up from the same measure. Here we're focusing just on measuring things. And so what is measures library? Measure library is simple functions where you input data in there from the data storage that we have, and you calculate. I mean, measures library will calculate a measure or multiple measures. It's highly composable because you can write a measure and then write another one that builds up onto the other measures, like Lego bricks. It's easy to contribute because it's kind of centralized, and also you have kind of a standard framework to deal with. So you don't have to have a multitude of different ways of doing things. And also it's efficient. So there's a spoiler here. It's about caching. We'll come back to it. So let's define a quick, super simple use case. Here I just picked the playback logs and the UI logs from the previous schema. So those are sources of data. And we'll calculate play traces out of playback logs here. And what are play traces? Play traces are events such as start, play, pause, play again, reposition, skip, rebuffer, etc., etc. Those are the events as they happened on the device, and it's supposed to make a representation of how things went on the device and how it impacted the user. And from them, we can, from the play traces, we can calculate other measures off of that. So that's what I meant with composability. We can calculate rebuffer counts, so how many rebuffers happened during that session. Play delay, so the delay from the start and the actual play. And then we have something that is more like a dimension, but device models. And what's interesting with the device model, for example, like a Samsung TV or something, is that we can derive that from multiple data sources, so from UI logs or from the player logs, like the playback logs. All right, so let's define some model here for play traces. It's massively simplified. It's like actually really big and across multiple files, but let's define the thread play trace, and it has an instant, which is the time that that play trace happened on the device. And then you have a few implementation like start, play, rebuffer, and those have a lot of information. But for example, rebuffer, I just kept the one for rebuffer. It has a reason, because a rebuffer can happen for a multitude of reasons. Because of network, you might think it's always network. It's not always network. It might be the CDN that was not available at this time. It might even be your device. In fact, the reason is actually not just a string. It's more complex than that, because you might rebuffer for many reasons: for video buffer, for audio buffer, or even time text, which is subtitles. Subtitles can trigger a rebuffer. It's possible. And then what we tell people is create a file, for example, playtraces.scala, and then define a type. Here, it doesn't have to be an opaque type. I used an opaque type here to define, because it's like when it's a simple-ish, there's simpler cases that I'm going to show you after, but you would use an opaque type. So here we just created the playtraces opaque type, and the implementation is a sequence of playtrace. We also made it extend sequence of playtrace so that you can just like use it as a collection, basically. And then we define a companion object, and in the companion object we define a given of parser of play traces. So parser is the type that we use for calculating, representing the calculator kind of the measure, and the measure is play traces. And we can see this one as a dependency on session on playback session. So it needs, in order to be able to calculate a parser of play traces, it needs a playback session. And then we're using that session. We just get like, let's say there's a field player logs, and we use that. And then I didn't put the implementation here. I just put like a function, an imaginary function that is parse play traces. But in fact, this is for in our code base. It's actually on multiple files across multiple packages because we're doing a lot of things. We're parsing the logs are in JSON, so we're parsing the JSON. We support TVs up to more than 10 years old. So you can imagine that some TVs are not logging correctly. Some features of the logging were not there, and so we have to be back compatible for like a long time. Network issues might corrupt the logs or not have all the logs that we want. Like for example, you have a rebuffer, you never had a resume, but you're still playing. You receive events that is still continuing to play. So clearly, some logs were dropped somewhere. So we're patching that. We're doing a bunch of sanitization there that we don't have to dive into it for this presentation. But all you have to think is that it's a little costly. So you don't really want to do that too many times. Just once per session, it's enough. Here's another example from the schema the schema that I showed you. Rebuffer count. So this is no big type of an int. It's just an int. The number of rebuffers. And here, what's interesting is the play trace. The parser of rebuffer count is depending as a dependency basically on another parser. So you can put here another parser, such as the play traces, and then we're just using it. And to use it, we just do play traces, empty brackets, and I'll come back to why empty brackets, but this is how you get the, you call the apply function basically, and it will get you play traces. And then you can do count, I don't know, as instance of rebuffer, for example. It's a simple implementation that I put there. Another one is the play delay, for example. And the play delay is a finite duration here. And it also has a dependency on play traces. And note that this one, the play delay can be not there, just none. So it's wrapped into an option. And then I put some implementation here, but we don't really have to dive into it. But the reason why play delay is optional is because what if you started the session, like you actually asked for a movie, and it never actually played? So there's no such thing as play delay because it just never played. And the last one, which is device model, it's a string. And what's interesting is that here we have two parser with two different dependencies, which corresponds to the graph that I showed you earlier, where basically we have, it can be calculated from two different sources. So here we have two dependencies, one from playback session and one from browsing session. And it's just extracting a field. This one is doing nothing, really. All right, so once you have this code, all those measures and so on, you would basically deploy it on the app. So you would have the apps here depend on measures library. And I guess the requirement is going to be like, it has to be JVM, hopefully Scala, but like, if not, it's Java. And so there's two parts of the library. There's like the part where you write measures, as I showed you, and the other part is we call them the runners. So those are the Spark and Flink apps are runners. And so here's how the runner would run it. You would define a case class, which most likely is going to be your schema, and that's why it's a snake case notation, because most likely this one is going to go to a table, and this is the standard way of writing the data there. And then, so here, this one is going to be reading for the playback session source. And so I put triple question mark here, but you would basically have like some decoding of the data, like whether it's JSON or Avro or whatever. You decode that, put that, create the playback session class. And then you call measures library by calling the apply function of parser of measures, that case class. And as long as you have a parser for each of the fields of the case class, then it will derive one for the case class. And then we can match on it. And if it's a success, then we get the value. We can also have issues with it. I'll come back to that later. Or it's a failure if there is like any exception. Then you have the exception. You can log it and go on with your life. Another precision here, you can see that we've wrapped everything into options here, even though other than play delay, they're not necessarily options. So I'll come back to that also later. So what are the pros here of this API? What have we done, basically? We don't have any really functional concepts. There's no real flat map and so on of, at least maybe for the option, but at least not for the parser. We didn't have, when we had the dependency here, we didn't have to have a full comprehension or play traces.map or flat map or whatever. We just use it as is. So it's kind of, I guess you got it right. It's direct style. So why is it a big deal? Because, like I told you, we have a bunch of people, front-end, data scientists, and so on, that don't necessarily understand Scala, and they don't really have to learn all those functional concepts to be able to understand the code, at least to read it and understand, and maybe potentially even to write it. So the onboarding would be easier. You just define, you might not understand like what is an opaque type, but if you read the documentation, you just like, tag along, and you might not understand what is a given and what's going on, but if you just create a companion object, create a given, and you're being told that you define dependencies here, and it looks like a function, I mean, it's here, and then you get the parser, you should be able to survive. All right. So how does it work? Let's have a look at the backstage of it. The inside of the API. So we're using the boundary API. It's been introduced in a few talks today, also in Martin Odesky's keynote. So that's helpful, but I'll try to explain also how we use it. But before, here is how the parser is defined. It's actually an enum, and it has two cases. So one success and one failure. And here you can see the success will give you the value, and issues is iterable or throwable, and failure is an exception, throwable like also. And then we also have this apply function. That's the empty brackets that you saw on the play traces to get the play traces out of parser. So basically, when you call this apply function, you'll get the value. That's it. However, you can see that it requires a label of failure implicitly. And this is because if it's a success, then we'll get the value, we'll give the value to you. But what if it's a failure? Then we'll use the break from the boundary API, and that one requires a capability of failing. Like that's what the label of failure is the capability, I guess. And it's also making sure that you can call apply only within another parser, as we'll see later. But basically, if you break here, you're sure that it's going to be code upstream. This is the companion object. So the companion object has an apply function. I didn't talk too much about it, but we defined somewhat of a boundary here. Let me come back here. We have a parser colon here. I didn't talk about that too much, but you're calling the apply function here on parser. And so this is this one. This is this apply function. And the body is actually giving you a label of failure implicitly, or it's a context-bound function, I guess. And so you actually, within the parser, you actually have a ability to fail. And if you call like play traces and play traces fail in your rebuffer count, for example, that's gonna fail your rebuffer parser. So all of them are gonna fail subsequently. We also have another given for, so basically if you have a parser of a value, we'll provide you a parser of option of value, which is always going to be sum. So it's useful for some, you know how we define the class here, the measures class, we defined options. So if you have an option there, we can fill in a sum in there of your value. Lastly, we also have a parser for any product type. I put question mark here because this is using shapeless free, and this is a whole different talk. I won't be able to fit that in the time that is given to me. But that one will actually, if there is one of them that is failing, it will fill in the case class a none there, so that you don't crash the whole case class, basically. That's why we were putting options there. And that's it. I mean, that's pretty much it. The API is pretty much fitting on the slides here, on 2 slides. So I'll go into optimization now, because we had issues with it. There's one thing that I forgot to mention, is in the component object of parser, we did define an apply function, which is basically just a shorthand so that we don't have to do summon parser of whatever you have. And we did that, and then when we run the app, let's say this one, it just crashed instantly and it was not working at all. And so let's see why was it failing. So I'll just expand how the implicits are getting, or like the context bound parameters are getting wired here, and let's remove the code above and below the yellow stuff and format it somewhat. So it's not really true that it's going to be like that, but basically for the purpose of this talk, we can simplify it and flatten it. But basically, the first given parser value is for the case class measures, and it has 3 fields. So I guess it's going to have 3 calls to each of the parsers of those types. It's not really going to be flat. It's going to be recursive, but for simplicity here, I just put them flat. So the first field was rebuffer count. The second one is a play delay, and the last one is device model. So to calculate rebuffer count, it needs, because it has a dependency on play traces. And so we call play traces once. And play traces is depending on playback session. And after, for play delay, we also need play traces. So we're calling play traces twice. And remember, it was expensive. And also remember that we have like more than 750 of them. So if we start calling play tracing and calculating them 750 times for like, I don't know how many millions of users we have on Netflix, but it's a lot. So that's why the app instantly crashed. So we started to look into caching, and we implemented something with a map. We were hashing and putting values into the map and like getting the key like that. And it worked. It actually worked pretty well. But then I ran a flame graph. I don't know how familiar you are with flame graph, but it shows you a graph of how the dependency, so how much time you spent either in CPU or memory. And I saw that we were spending a good 20–25% of the time hashing, just to store and access values in the hash map. So I was like, okay, can we push that caching at compile time? And so I ended up writing a macro. I'm not going to show you the macro again. If you really want to see it, you can come to me later. But I called it summon cached. And what this is doing, it's doing the summon for you. So obviously, you have to inline this function. It summons the parser for the value that you have. And then once it has it, it rewrites. So like it would be that what we saw right here. And it would rewrite the calls more like this, where basically it puts every call into, or like at least the calls that have been called twice or more, into a val, and then it would fill in the val in there instead. So it's like just cached, but no key, no hashing, nothing, and we save 20 to 25% of CPU with that. So that's another usage that was pretty cool of macros. So in conclusion, direct style, we're using basically direct style for easy contribution, which is really nice because we have this population of users that are not not necessarily functional programmers. And we use givens for automatic wiring of everything, which is a bit better than Spring wiring. And because it's at compile time, so it would fail at compile time if you don't have a parser for something that you were thinking that you have one. And we're also using opaque types for zero runtime overhead. So that's pretty nice. We can, because most of the time we're dealing with like ints or doubles or primitive types basically. And yeah, we used macros for better caching. So one work that we've done after that, we wanted to build this UI that I showed you. And we actually did. It was mostly AI generated, I have to admit. The UI looks like this. But basically, I wrote a macro for that would analyze the code, the chain of calls of givens, and it generates compile time. It generates a file, a JSON file that has basically represents this tree. And someone in my team coded that UI. It's not Scala.js, but it's just TypeScript. And every time we deploy, we have a new JSON file that gets uploaded, and that graph is like interactive. We're planning to add links to GitHub, so it improves like discoverability. So you can browse that and see the dependencies, click on like play traces, and you would be able. We don't have this feature yet, but you would be able to click on a link that would get you to GitHub to the exact line where this is defined. Also, in the future, we'd like to use pure functions because I didn't mention it, but since we're caching, we're not supposed to do side effects. If we can enforce it at the type, that would be nice to change that double arrow greater than and sorry, equal greater than by dash greater than for the function. And that's it. If you have any question.
So my question is of the Scala 3 new features, syntax, etc. What are those that you see go better with the rest of the non-Scala folks to be able to, like, what are the easiest for them to learn and work with?
Yeah, I can mention some. I mean, for sure, anything that enabled direct style is helping. So I guess the boundary API with the context bound functions, that's helping. We also, unpopular opinion, but we have a lot of Python developers. They're not used to brackets, so we mostly don't have brackets.
I'm okay with it.
Anything else? I think those two are the highlights.
So it means that you're already using the experimental features, because if you are using the label notation, all of that, yes?
Sorry, say again?
So since you were passing the labels as using, it means that you're already using the experimental features?
No, I don't think so. It's not experimental.
It's already... it's in the library already? Oh, okay.
Yeah, it's a standard library. Yeah.
Okay, good.
I think it's in the standard Scala free library, not.
You mentioned external contributions done by people not familiar with Scala. Is there many of those, and do you see much of cargo culting? Everybody copies opaque type, etc.
Yeah, it's not easy. It's not all pink. Adoption is like, I mean, I would say there is also, yeah, people are not necessarily like as passionate about the language features and all that stuff. They're more passionate about actually answering the question of like, did we progress the player? You know, is the player performing better and so on. So Scala is kind of doesn't have to be Scala. Whatever the tool is, it's in your way of answering that question. So we need to make sure that it's there's as less friction as possible into this thing.
Thank you.
At the beginning, you show some scenes that you say it could be one could be shown at a lower quality and other could be shown or must be shown at higher quality. So the question I have is that automatic or is pre-marking the videos? Because I guess it would be too much job to just mark every scene.
No, so basically at encoding time, the scenes are it's all automatic, but they're scored. It's open source. It's called VMAF. What does it mean? Video multi-factor. I cannot remember, but basically that score is the higher the score, the more detail and the more likely your human eye will notice a downshift in quality. And so we chunk we chunk scenes and we assign a score on that. And so the adaptive streaming engine is able to, it knows all the scores of the scenes upcoming, and it will make decisions, clever decisions based on that.
Are the chunks of a fixed size or is variable?
No, it's maximum 10 seconds, but can be lower if it's easy to detect the end of a scene as soon as the camera changes on something else. It's like it's a new scene basically.
Great, thank you.
There's one over there.
Thanks for the talk. That was really cool. Actually, I have a question about the emitting of the events. Like, are those capable because because there are so many different devices, right? And is it because like there's a specific player or like a custom player that y'all are using that can send these events, or is it native to every? Yeah, is it native to every device, and then you have to implement this kind of thing? I don't know if that's too secret for now.
We have that's you're talking about the play traces event.
Yeah, so like how do you you're defining all these events, and then like the ones like for it's buffering, and so the device has to emit it, right?
So we get most of the data pretty accurately on every devices except Apple, because Apple devices you have to use their SDK.
Right.
So that's why usually you would have a lower quality of experience on Apple devices than other devices. Like on Android, you would usually have a better experience.
Okay, thanks.
Hi, thanks for the talk. I was just wondering, are you guys thinking about, because as I see it, this is mostly sequential, right? Like there's no parallelizing or using concurrence to optimize?
No, there's nothing. But I mean, there's nothing because this is running on Spark or Flink where it's massively parallelized. So it's not like I guess the act of calculating those measures, we call it summarizing. So a summarization can be all sequential. We're gonna be like parallelizing like crazy on all the sessions that come in.
Okay, yeah, I understand.
It doesn't need to be parallelized really.
Thank you. I'm not sure if you're allowed to answer, but is Netflix committed to Scala 3, or do you have a little island of Scala 3, and how have you been cutting over?
I'm not allowed to answer it, but yeah, it's an island basically, yeah, of Scala 3. I think In general, we don't basically internally. Scala is community supported. That means we're supporting it between each other. We don't have a team dedicated like Twitter that supports the language internally. The closest to it is we have Netflix is pretty much a Java shop. So we have a lot of Java, and the Java team will support somewhat up to the JVM, not into the language. So once you have a jar and things running, they will support that, but they won't go into the language stuff. And then we have a big data compute team that maintains, Spark. We also have another team that supports Flink. Those two, they will do somewhat of support for Scala, but that's it. For Scala 3 on Spark, they don't really want to support it, but for obvious reasons, because even Spark does not really support it. So we do. There's a few jobs that are mostly the ones that I introduced, to be honest, that are using Spark on Scala 3. But Flink maybe a bit more. There's quite a bit actually, but that's it. Yeah. Otherwise, it's 2.12, 2.13.
I have actually now a second question. So since you are talking about measures, that this toolbox to actually measure and to optimize for Netflix and stuff, is there actually a way for you to measure how Scala performs in a way to justify using Scala against other languages for the same kind of task?
And I'm guessing performs you mean in terms of developer productivity or runtime?
Well, it's harder to measure feature delivery, but the stuff that you can actually measure, like resources it is used to get everything done. So performance, yeah.
But yeah, developer, like how we ship product or like new measures and so on in time, etc. Or
okay, so I will rephrase. Basically, if you are able to measure your Scala code against the Java code to justify to keep certain stuff being done in Scala, or if it's just coming part with.
No, we've never. I mean, we've never tried that in Java, so I wouldn't even know what would it be in terms of performance. But I would assume it would be somewhat similar. I don't think. I mean, okay, if you have to go into, I don't know what it would look like in Java really, but if you have to have like this kind of like, I mean, we're relying on givens for automatically wiring everything so that people don't have to care about that. How would you do that with Java? You would probably like, can you do that with Spring? I don't know.
So your choice in this case to justify Scala is because of the ergonomics for the engineers.
This code base before this API was already in Scala with a different API, completely different, that had too many limitations. So it was already in Scala, but the justification for using Scala even outside of this API or even outside of Scala 3 is because Java, I think it's on the data side, it's too verbose. I don't think people are even discussing things and do anything in Java on the data side, to be clear, because on the backend side, it's all Java. However, there's a discussion between Python and Scala. That is definitely a discussion. So obviously, you want type safety, and there's no such thing in Python, or like there's a little bit, but yeah. So yeah, there's definitely a push internally to also use Python. Maybe I have measure library done in Python, or especially data scientists, they like Python.
I kind of have a follow-up question. The data comm is really interesting. Like, so you're using Flink. Are the Flink folks using Scala with like Flink extended, or are they still an old Flink version, or how does that work?
So that's an interesting question, because with Scala 3, there's no choice. It's with Flink extended. But any usage below, I know Flink dropped Scala support for actually enabling us to be able to use whatever Scala version we want. Our internal team actually extended the support for it, like they're pushing it to 2.13. So majority of jobs that are on Scala 2, they're using the I guess the open source one that has been removed from the open source Flink, but it's being maintained into the internal one. But they will, for Scala 3, they're not gonna support it, so it's slowly switching to extended.
So, if there are no more questions, let's thank Joan again.
Thank you.